Good morning, I guess good evening, good afternoon, good morning, depending on where you are. This is Manish Gupta. It's my real pleasure to welcome our third keynote speaker for the conference, Professor Sunita Sarawagi from IT Bombay. Sunita is an eminent researcher in the area of databases and machine learning. She's an institute chair professor at IT Bombay. Sunita got her PhD in databases from UC Berkeley, and I've had the pleasure of knowing her since her grad school days, and a bachelor's degree from IT Kharagpur. She's worked with Google Research, CMU, IBM Alberton Research Center. Last year, Sunita was awarded the prestigious Infosys Prize for Engineering and Computer Science, and she's also been awarded the Distinguished Alumnus Award from IT Kharagpur. Sunita has several publications, including Best Paper Awards at ACM Sigmod, VLDB, ICDM, NIPS, now called NeurIPS, and ICML conferences. So these are really the top-notch conferences in machine learning and database areas, and she has Best Paper Awards, not just papers at these conferences. She has served on the board of directors of ACM SIG-KDD and VLDB Foundation. Sunita was program chair for the ACM SIG-KDD 2008 conference, research track co-chair for VLDB 2011, and has served as program committee members for SIGMOD, VLDB, SIG-KDD, ICDE, and ICML conferences. So without further ado, let me hand it over to Sunita, who will be talking about modeling multidimensional correlated temporal sequences. So over to you, Sunita.
Thank you, Manish. It's really a privilege for me to be able to talk in this conference. Even though I am not really like a researcher in this area, although my PhD was in databases, I have been working on machine learning for almost 15 to 20 years now. And I was trying to find a topic which would be of interest to this community. So I thought of presenting some work we have been doing on handling temporal sequences of all kinds over the last 3-4 years. So as you all know that modern deep learning has gotten a lot of press because of the absolutely impressive accuracies that they have obtained on various tasks having to do with images, text, as in natural language processing and speech. But somehow temporal sequences are not considered mainstream enough. But I thought in this community, data which have time as a primary component would be of great interest. So I'll take you through some examples of what I understand as temporal sequences. So we'll be considering two kinds of temporal sequences. One is regular time series. You see an example of a regular time series up on the top right hand side. So this would, for example, be the kind of data you would get if you were recording daily traffic on individual web pages of a site, a website, for example, Wikipedia. They have a well-known Kaggle competition where they have provided web traffic to their individual web pages. And this is a task which is quite popular. Another example could be that you have hourly load on various servers for different applications that are run on that servers in a data center. I got interested in this problem in a more commercial setting where we were interested in doing demand forecasting for a large e-retail organization, in particular Flipkart. So that is basically examples of regular time series, but by temporal sequences, I would also like to include irregular event sequences. So again, in the context of this conference, people might be interested in modeling the time when a user is likely to return to a service. Again, another famous data set is where we have user visit times to a music service, and you might want to predict when the user is likely to return, how long will the user stay in that session, and what are the set of songs that the user is likely to play. Other examples of event sequences would be like event logs. So you might have different kinds of alarms, and alarms have a timestamp, and then there is a type of the alarm. In general, attacks on a system. There is again another well-known data set in KDD on various kinds of attacks on systems, which can also be modeled as temporal event sequences. So basically in the regular time series case, we partition time into regular intervals, and here, the time of an event is the variable that we would like to predict. So, so both of these kinds of data we can represent as temporal sequences, which are basically sequences of 3 tuples, where the first component is time and the second component would be like a vector of features which are associated or associated with that time or otherwise provided by the user, and you have a value which, for example, in the retail case could be the total demand on a product, the total amount of units sold of a particular product. And you have a whole sequence of this for a particular series, and we are interested in the case where our data set consists of a collection of series, so a collection of such sequences, and we are going to denote index the sequences by the superscript I. And in my title I talk about multidimensional temporal sequences. So this index space I could be multidimensional. Again, going back to the retail example, the index space I could correspond to combinations of product IDs and regions in which a product is stored. So if we are considering again the data center example, it could be like the index could correspond to a server and application combination whose load you are wanting to study. So this is the data that we are talking about. Now, on such data, we want to accomplish various tasks. So one very well-known and popular task is forecasting. But, repeating this very cliched quote from Niels Bohr that forecasting or prediction is very difficult, especially about the future. So we cannot hope to make exact predictions. So therefore, we would be interested in probabilistic forecasting. And there are 2 types of forecast that people have sort of thought about separately in the ML literature. One is short-term forecasting, where you have seen data up until a particular point in time, and you're interested in just predicting the very next value. But we would be more interested here in long-term forecasting, where you're given a range of time in the future for maybe you're interested in forecasting the sales of a product over the next 8 weeks. So we would in general be considering this forecasting problem in a situation where for any given series we have a known history and then we have a forecast horizon, and we are interested in predicting the values of the series in that forecast horizon, and not just a point value, but we want to assign a probability with over the different values, and that probability here you see indicated by the gray region. This is for regular time series. Equivalently, when we have event sequences, we might be interested in forecasting both the time of events and the type of event in a particular forecast horizon. So here again we are given a history of events. So here each the x-axis you can think of as a time axis, and the color of each of these bars indicates the type of events. So we are interested in predicting after a given time t, which could be like say the present. We are interested in predicting the time of all events up to say some end time te, and also the types of those events. And again, we would not be exactly sure of the time of the future events, and we would want to make probabilistic forecasts. So this is the forecasting task. But again, for temporal sequences, particularly when you are doing data analytics, a lot of other tasks are important, like outlier detection is another common task people want to accomplish on multidimensional time series data. Missing value imputation, very often for some reason in your system you may not have collected logs for a particular period of time, but you still want to run some data analytics. So can you impute those missing values? But in this talk, I am going to focus on long-range forecasting. But the good thing is that the key modeling questions like how do you create this probability distribution which would predict values. It could be values which are in the future or values in some intermediate point. The key modeling questions do not change much. So many of the things that I'll be talking about in the context of the long range forecasting task would also carry over to, for example, the missing value imputation task and also the outlier detection task. Essentially, an outlier is something which strays away from what the model thinks is expected. So this is our situation, and of course, forecasting, it's an age-old problem. There is like some 100 years of work on this topic. So there is a rich battery of methods in the statistics community. You might be familiar with terms like ARIMA, Box-Jenkins method, exponential smoothing methods. So there are many methods which have served very well. For example, financial time series data. Most of the statistical methods, they reason about a single time series at a time, so we can call these as local methods. So they take a single series and then they create a sort of a model with few parameters. Maybe you might model the seasonality and trends in that time series, and then you can use those few parameters to predict and do the forecasting. But most of them are not, because they are local models, they cannot handle non-stationarity very well. And although some of them can take as input features attached with each future time, they are not very powerful in terms of handling nonlinear dependencies between the input features and the output variables. And also, the methods often do not handle interaction across related time series. There are also state space models, for example, Kalman filters, but they make simplifying assumptions. For example, a linear Gaussian dependency between the input features and the output, which may not hold in practice. And of course, traditional machine learning have many powerful tools. For example, kernel methods and gradient boosted regression trees, which have achieved really good accuracy on not just time series, but also general classification tasks. And there are methods which have been developed specifically for time series, like a version of boosted regression trees, which does also some linear fitting at the leaves of the decision tree. We'll be talking about that method called cubist. And so these methods essentially take this two-pronged approach, that first you use your domain expertise to featureize the history. Examples of such features could be like, say, wavelet coefficients or Fourier coefficients, which you derive from the data, and then you just convert it into a regression problem. And these are often very powerful and they work quite well. But like what we have seen, for example, in the case of image classification, like the famous ImageNet challenge, where for a long time people had been working with handcrafted features like the GIST features and using support vector machine classifiers to get an accuracy, and then suddenly deep learning came and smashed their records and achieved much better accuracies. There you did not depend on hand engineered features, but you used deep learning models to learn representations from raw data. So the question is, can the same thing be done for temporal sequences, for time series data? Actually, you might be surprised that for time series data, the gains deep learning provided on came much later than on images. So for a long time, I would say up until 2017, it wasn't clear whether deep learning would improve over established methods for time series forecasting. And this was roughly the situation when when we started working with a bunch of Flipkart researchers on the problem of demand forecasting. So our task was to predict inventory of a huge catalog of products, say like 100 million products, and we would have to predict the inventory for the next 8 weeks, and then the prediction has to be done for a particular product across different regions, and there are a very large number of confounding factors which make the prediction extremely challenging, as you can imagine. There are products of very different scales of demand, and within a particular series there is a lot of variance in the output values. So and people had been building forecasting models using conventional methods over such challenging data set, and they were up to a point when they decided to investigate deep learning methods. So just here in this slide you will get some glimpse of the number and variety of features that are available for demand forecasting in a large e-retail house. You will get some idea here. So for example, here you have features which characterize different properties of products, and then some set of features which are like product visibility features, like whether a sales event is held on the product, and whether it was advertised on the home page or not, various properties related to the price of the product, what kind of discount is being offered, and so on and so forth, various properties of time. So what we are calling as the input features are very important, and that's why it's important to have a model which can handle powerful dependency, which can model powerful dependency structures between the input features and the output variables. So when we talk about neural models, so naturally recurrent neural networks, when we are talking about sequences, have it's a natural choice. So that's what we did. So we had like a multi-layered neural network where we would summarize the history part of a given time series using a recurrent neural network, and the rich set of input features would be first transformed through embedding layers and other multiple layers of feed-forward networks, and then they would be fed to multiple layers of, say, an LSTM network, and finally from that RNN state you would want to predict a distribution over the output, over the predictions that you might want to make. So there are different ways in which you can parameterize the output distributions. For example, a simple choice would be to just impose a Gaussian distribution over the output variable, and in which case from the last layer of the neural network you would be outputting both the mean and the variance of the predicted variable. So you don't just give 1 point predicted variable, but you characterize that predicted variable in terms of the parameters of the distribution which reflects uncertainty over that variable. So that could be one choice, but we will see that a single Gaussian would not work for challenging data sets like in the case of a large retail organization, and we had to use something more complicated like a mixture of Gaussians. Other people have also tried to directly output quantiles of the predicted distribution. With quantiles, the advantage is that you are not making any modeling assumption. You can handle any distribution on the output variables. So this is the neural architecture. And as I said, for the case of this Flipkart data set, the single Gaussian was not sufficient. So we had to use a mixture of Gaussians. And in order to model a mixture of Gaussians using the neural network, the last layer of the network would output 3K parameters. So if you have a K component Gaussian mixture, so in our case we used 10 mixture components. So we would output the weight of each of the mixture components and their mean and variance. So with that, you could, for example, you could output the distribution that you output could be multimodal, like you see in this bottom right hand side of the slide. So this was the output layer, and finally, if you think this is of the network, this is another view into the neural network that was trained. So at each point in time, you have a whole vector of input features, and these were embedded and fed through multiple layers of feed-forward networks. These are called the associative models into RNN cell, and from that RNN cell's state, you output mixture components, and on that you apply a mixture of Gaussian density loss to train the model. So the nice thing is that once you parameterize your model in this framework, you can train the whole network end to end, and you are essentially capturing the full joint distribution over each predicted variable in terms of the parameters which you extract from the features at each point in time and the history at that point in time. So this kind of a maximum likelihood training is quite principled, and it can handle a flexible set of distribution, and this is just standard machine learning, and you can train this network end to end jointly over all series. And the likelihood model here is also quite efficient to train, and it parallelizes easily, because when you are writing the likelihood term for the jth prediction, you assume that you know the true values of all the occurrences up to j minus 1 point in time. So this is the training, and here you will see some glimpse into the kind of results that were obtained. So we found that the neural methods provided much better accuracy than a highly tuned over multiple years non-neural method, which was based on gradient boosted regression trees. So this method is called cubist. So in here you see on the x-axis different product categories, and on the y-axis you see error. So higher is bad. So the green bars denote the traditional machine learning regression tree types method, and the gray bar denotes the neural method, which is the autoregressive mixture of density network model that we were calling ARMDN. And you see that in most cases the gray bars are lower than the green bars in terms of error. And here are some cherry-picked time series from the data sets. So you see that the green part denotes the true value, and the vertical line separates the known values from the predicted values. And the neural method, which is again called ARMDN here, which is this purple line, provides in general predictions which are closer to the true values, which are these green lines, compared to the blue lines. So you see this in all 4 time series. Okay. So in some cases the difference is quite stark. So you see in this bottom right time series, you find that the predicted value is flat, whereas the neural method is able to predict the spike here, and that spike was because of it's sort of a totally explained spike that happens for that product around a particular time of the year, and for some reason the ML model, the traditional ML model, was not able to capture that dependency, whereas the neural model could latch on to the features which cause this periodic spike on that network. So this was a good story, but then we started getting more and more interested in the problem, and we asked, are we done? What more can you do to improve the model? And from then on, so this has been like almost 3 years since we have been working on various ways to improve that model, and not just us. There are many researchers worldwide. In fact, there is a very active team in Amazon Research in Seattle, which they have been writing many state-of-the-art papers in this area. I'll be discussing one very exciting recent papers of theirs towards the end of my talk. So now, what are the ways in which you can improve this method? So one big tension that we saw when we tried to train this neural model on more and more data sets was that, yes, there were many cases where the neural model was not able to do as well as even the classical statistical models, which we are going to call the local models. So from now on, we are going to call the neural models as global models, because though the parameters of those models are trained over all the series in your data set, as against the local models where you derive their parameters only from a specific series. So we found that there were also many cases which we could pinpoint, where the local models performed much better than the global models. So we are going to first discuss this issue of whether, what are the trade-offs between the old style statistical local models and the modern neural global models, and is one always better than the other? Can you kind of combine the two and somehow get the best of both worlds? So that's the first point. Then the second point was about the performance of these models when you really want to do long-term forecasting. So in the problem just what we presented just now, we are doing only 8 weeks into the future forecasting, which means we would be making 8 predictions into the future. Now, very often one is interested in making predictions which might span for a much longer period for planning purposes, like maybe 3 months into the future. So are these models good enough for such long-term forecasting? And we will find that they in fact do not perform very well. They suffer a kind of gradual drift, and we provide an algorithm for fixing those drifts. And finally, even though in the title of my talk I said we want to handle correlations, and the statistical models do not capture correlations across series, the global model that I just presented, even though it is trained jointly over all the series, finally it outputs a distribution only over a single series at a time. So, but very often you might be interested, say, in joint distributions over collection of interacting series. Very often, like say, you might have cross-selling and co-evolution of products, where you might be interested in capturing correlations. So here is an example of how the global model could miss local patterns. So you see 4 time series. This is another real data set. It's called Rossmann sales data set. So here we train these models within IIT. Similar model to what I presented from the Flipkart example. And here you see the black are the real values and the red are the predicted values. Now, if you just were to look at the black values, they are very periodic and they follow a pattern, and it seems frustrating that this all-powerful global neural network cannot capture these regular patterns, these regular spikes that are very much present in the history too. You see the same issue in the second time series and all 4 time series that are presented here, that the global model somehow misses the patterns which very much appear in the history. So is it possible to somehow learn local models while also maximizing the sharing or the learning that you get out of joint training of the global models? So that was the question that we asked. And, this is I was also interested in this problem because it's an instance of what in ML is called a domain adaptation problem, which has lots of applications. And I have been working on this problem for many years. So, a domain adaptation problem arises when you train a model, and in deep learning that is quite common because for training a deep learning model you need huge amounts of data. So domain adaptation problem arises when you train a model on a data set T, which is huge, and it is obtained by unioning data from multiple users. In our case, users can be thought of as series. And you train this global model parameters theta, and now when you try to apply it on each user or each series, then you don't get its optimal performance. But each user or series has a limited amount of label data. We are going to call them Li. In our case, that limited label data comes from the history of that series. So can we adapt or personalize theta to each user? So this problem is also called a personalization problem or an adaptation problem, and many solutions have been proposed. A standard thing that everybody does is to start with the global model and just fine tune that model. So you just run a few more steps of gradient descent, just do a little bit more of training on the global model using your user specific or series specific data. But we found that when we applied that domain adaptation fine-tuning idea for time series data, number one, each time series actually has not that much data. It's really like a pathetic amount of data. So it just does not get enough reliable fine-tuning, and it has a huge amount of variance. So that didn't work. And another paradigm which is floating around in machine learning a lot is the concept of meta learning. So during training, I don't have undifferentiated IID data, but I have groups of data. So in our case, we know which instances come from which series. So when you have multi-series data, can you learn to adapt? So this is called meta learning. And again, many methods have been proposed. So one very popular method is called MAML. So MAML kind of tries to learn a single or a few adaptation steps from local data as an inner loop of an outer shared model. So this, it sort of sounds very neat, but when we tried to implement it, we found that it was very unstable. It didn't work very well. And then subsequently, other methods have been proposed for such domain adaptation. One such method is snail, and that method, sort of does some kind of self-attention over the label data of each user. So that was sort of better than MAML, but still not as good. Another method which is only possible in deep learning is what is called the deep state method, where the whole idea is to generate per series parameters using another neural network. So it's like for each time series you will be using a Kalman filter, but the parameters of that Kalman filter will be obtained using another neural network. Okay, so that was, again, it sounds very exciting, but we found lots of failure cases with even the deep state method. So instead, what we proposed is a very simple idea that let's partition the set of parameters that we have to learn into the set of parameters into what we call as shared parameters, which would be learned globally across using over all the series. And then for each series, we will have its own parameters. So let's say that for series 1, this is the pink series, the green series, the cyan series. And actually our method allows us to learn parameters even for new series which have not been obtained, which have not been seen at the time of training. And we avoid the MAML kind of nested loop training by making the series specific parameters derivable in closed form. So for training the series specific parameters, you don't need gradient descent. You can obtain the optimal parameters of each local series in closed form. And also the kind of closed form parameterization we achieve, those parameters can be obtained from the data in one pass. So the sufficient statistics required to generate local parameters can be collected in one online streaming pass. So this method therefore we call as adaptive recurrent neural units, and I will be describing a bit more on what that method does. So the main idea, as I said, is very simple. The per series parameters, we are going to actually let them be the parameters of a least square fit of the last linear layer of the RNN. So, the last linear layer, which was earlier just producing the mean of the distribution, using shared parameters, now just that last layer parameters would be series specific. And because we are dealing with regression problems, the optimal values of the last layer can be obtained in closed form without using gradient descent, because we all know the textbook solution of the optimal fit of a least square method. So we will just use that optimal fit of the least square method to get the series specific parameters, and the sufficient statistics required to compute these parameters can just be obtained from first and second order moments of the data incrementally. And these statistics we can now think of as a state of an RNN, and we can train the outer global model with this series specific local parameters obtained in a closed form using a gradient descent loop, which is very similar to what you would use in a baseline model. So this is we call this ARU RNN, adaptive recurrent unit. And so here, so this is just showing what we do, hopefully in a more helpful diagrammatic manner. So we take the last layer which we obtained from the RNN, and these are still trained using global parameters. And then the last layer is taken as input to, so this is the layer before the series specific layer, and these parameters are trained using least square fit using these equations. You don't have to go through these equations, that would be insane to try to go through this, but these are just standard least square fit equations. And then you get local predictions from the local model. But we found that it was necessary to finally combine the local predictions with the global predictions using again a second layer which was shared again across multiple series, and this is what gave us the final model. And that model actually somehow it was really amazingly good in terms of how easily it gave us accuracy gains. So for example, here we show the same series, and you see that we are able to latch on to the local patterns in all these series. And we compared with existing meta-learning methods, and we obtained much better accuracy. And also in terms of running time, we just are 1.5 times slower than the baseline, which does not use our unit. And our storage overhead is also of fixed size. We just have to, if the last layer of the RNN produces a vector of size 128, we would have to keep 128 square order space in the RNN to compute the matrix which will be inverted to compute the least square fit. So in summary, what we have obtained is a hybrid model which combines local parameters which suit each individual time series with global parameters which provide power and flexibility of deep learning. And our main contribution, I would say, was to come up with a way to represent the local parameters in a way that you can train them without disturbing the global training dynamics. and our method is not memory intensive also, because we have fixed size state. So this was one sort of enhancement we were able to make of standard deep learning methods. And next I'll be talking.
Interrupt. Sunita, about 10-15 minutes. Yeah.
Oh, 10 minutes left?
10, I mean, you can take a bit more, 15 minutes.
Oh, okay. Okay. So now we come to the second part on what are the challenges of using the neural models for long-term forecasting. Why do they not perform, and what can we do about it? So just for variety, in the previous part, I was illustrating with regular time series. Now we'll be talking about the long-term forecasting task for the case of irregular event sequences. So we are still talking about forecasting, but now our data type has changed to irregular event sequences. So here, but we have the same setup, that there is a history and there is a forecast horizon. In this case, for the forecast horizon, we are given an end time, and we have to predict both the times of the event, the time when the events will happen, and the type of the event. For example, you might be interested in predicting what are the times in which I am likely to get power cuts, and how long will the power cut last. Okay, so that would be like the type. It could actually, I'm loosely saying the type. It could be either discrete or continuous. So this is the event sequence data, and this we will be interested in this forecasting problem, and we are interested in situations where the forecasting horizon is large enough that the number of events that happen within the forecasting horizon is quite large. Maybe it will run into hundreds. So it's not like we are just interested in predicting the next 8 events, but we will be picking a time interval, say a week, and there might be some 200 events that will happen in that time interval. So the baseline solution for modeling event sequences is actually very similar to what is used for modeling time series. Here again, we try to train a model to predict the time of the next event, and again we impose a density over the time. For example, here we could have like a truncated Gaussian distribution, and the parameters of the Gaussian distribution are obtained again from the RNN state, like what we did for the case of time series. And from that distribution, we could sample a time, or we could just compute the expected time. And the time prediction parameters, as like in the case of regular time series, could be obtained from RNN state. And for predicting the event, again we could use the state and apply a softmax to predict a multinomial distribution of the types of the event when we have discrete event types, and when it is continuous, again we could cast it as a regression problem. So this is again our setup. Now, so this was the model which was quite popular in the temporal point process community. And when we got into the problem of long-term forecasting, a solution which has often been proposed is to just do forward sampling. So you have in forward sampling, you have trained your model, and at the time of inference, you predict the time of the next event after your time t. And once you compute a distribution, you sample a time from that distribution, you pretend that this is now the gold time, and then you predict the next distribution, sample a time from that distribution, and so on and so forth. So this is called forward sampling, and this is in fact surprisingly, this was the state of the art that people were doing. And it's not hard to see that this model could be subject to huge drifts when the end time is very large. So, and in fact, we saw that empirically here are 2 real data sets. One is a data set about tweets about elections. Another is a data about taxi arrival time in New York City. And on the y-axis here, you see the distance between the gold event sequence. So we measure Wasserstein distance of the time the gold events versus the predicted events. And as you go further and further into the forecast horizon, the distance with the gold is increasing. So, the reasons for the drift, it has been kind of analyzed, and we understand that the reason the drift happens is that during training, we condition on true values of previous events, and this is the sort of standard approach which is done in any autoregressive model. And this approach, even though it sounds surprising, is actually statistically sound. If you are just training, thinking of it as a Bayesian network, we have just maximized the likelihood of a Bayesian network. So it's statistically sound, nothing wrong with that. And plus it is easy and convenient to train and parallelize. So that's why it's really popular. But when you use it during inference in this mode, then you accumulate error because you're using it for multi-step forecasting. And this problem appears not just for event sequences, it's a very well recognized problem even in NLP, like when people try to train translation models, the same problem arises. And many tricks have been proposed. So one approach which is actually more popular in the event sequence community is to cast it as a sequence generation problem. And for generation problems, apparently GANs work very well for many people. Another option is to use sequence level loss functions, which you can train using reinforcement learning kind of objectives. People have tried hierarchical models and alternative network architectures like dilated convolutions, which capture multi-hop dependencies, for example, the kind which are used in WaveNet, a popular model in the speech community. And we found that those, of course, are better than the baseline, but they were still not as good. And we were able to come up with a method which was totally different from any of these other methods. It was just a totally different old style approach, which we call DualTP. This work appears in Wisdom 2021. So our approach is to train, it's like we applied multi-view learning. We trained two models, one which is the event model, which is the standard baseline model that I just presented. So that does microscopic modeling of the times of next events. But we in parallel had a different view to the sequences of events by also measuring through an independent model the counts of events in regular time intervals. So this we think of as providing a macroscopic view of the data. So in this way, it has some elements of hierarchies because we have a microscopic model and top of that we have a macroscopic model, but it's not quite hierarchy because the event model is modeling the time of the next event, whereas the count model is telling us how many events will fall within a particular time interval. So therefore, there is an element of multi-view learning also. So we have hierarchies and multi-view learning. And with these two components, now we train and we predict with both of these models independently. But at the time of inference, we achieve consensus between the two models in a way which is similar to how ensembling models achieve consensus. So given my limited time, I'll try to kind of quickly give you a top level idea of what we do. So we have this event model which is trying to predict individual times of individual events, and in parallel we have this count model, and the count model partitions this entire range of time into equal sized bins. So now we have a time series prediction problem, and within each bin now we are thinking of just estimating the count of number of events which fall in that bin. So this becomes like a time series prediction problem, and this becomes like an event time prediction problem. So the count model in fact is very easy to train. We could have used a time series model which is state based, but we found that counts can be modeled just by a vanilla feed forward network. That also is quite adequate. And the event model is an RNN like what we have been alluding to before. And the most interesting part of this work was what we do at the time of inference. So in one trend you will find generally in deep learning, people don't think too much about inference. Most of the effort is in training. It's like, and after that people do beam search or sampling. But some of us who have been working in graphical models, we feel that inference is also very important, and we saw that thought in action in this work. During inference, what we try to do is to come up with predictions which achieve consensus between the event model, which provides a probability distribution over the times of events, and the count model, which provides probability distributions over counts of events in future bins. So the consensus objective is a bit involved. So we have this first part which captures the likelihood of the event prediction model, and the second part which captures the likelihood of the count prediction model. And these constraints achieve consensus between the two predictions, and this can be cast as a constrained optimization problem. Stated here, the problem is intractable, but one can use sort of bunch of tricks from optimization to convert this intractable objective into an approximate algorithm, which is kind of where in the inner loop you just have to solve a concave quadratic program, constrained quadratic program, and it can be solved efficiently. We implemented it, and it works well, as I will show here. So we applied it on a bunch of data sets related to traffic, 911 traffic and election and taxi. So here you see some snippet into the data set. This is like actual event time trace, and this is the count trace of this data set. So we trained these two models, and we were surprised to get substantial accuracy gains. Unlike in the time series work that I presented, we obtained say maybe 10, 20, 30% gains. Here we are talking about orders of magnitude improvement in the reduction in Wasserstein distance between the predicted event sequences and the actual event sequences over a long-term horizon. And the chart that I showed you earlier about the drift, that is reduced drastically. So the red ones are what we were obtained from the standard forward sampling inference algorithm, and the blue is what we obtained through our joint quadratic programming based inference algorithm. We get substantial reduction in time. So essentially, in summary, what I presented was this unconventional method of capturing drift through two independent multi-view, multi-level models, which provide substantially more accurate long-term event forecasts than heavier weight deep learning machinery like GANs and all that. So finally, I'm just going to wrap up with the last part on how correlation is handled across series. So essentially, so far we have been talking about generating a distribution over the forecast of only a single series at a time. But now suppose if we are interested in capturing joint distribution over all your series in the data. Now there are two challenges in this task. First, if you try to model the joint distribution using a multivariate Gaussian, that's not going to be adequate. And for the case of single time series, we could use quantiles, we could use mixture of Gaussians. It's not very clear how you would do that with multivariate, with when you have like say millions of time series, what is a good joint distribution. And so the distribution, how to parameterize the joint distribution is a challenge. And second is handling the scale. How do you actually find out even what are the set of time series which are correlated? So recently there was this nice paper which appeared in NeurIPS 2019 by a bunch of researchers from Amazon on high dimensional multivariate forecasting with low rank Gaussian copula. And I will only be able to present a summary of the main idea in that paper. So their main idea is to first calculate cumulative empirical density of each series, and then learn a differentiable function to map each of these series to Gaussian densities, and once you have done that, you can use a copula function to express their joint distribution. And they were then finding it reasonable to use a multivariate Gaussian copula because each of these series have been independently mapped to look like Gaussian. And then thereafter, the challenge of scale was handled through a trick which is also quite well known in the Gaussian process literature, by having the covariance matrix be obtained through a kernel, say a dot product kernel of two vectors. and those two vectors are obtained as dot product of two vectors. The first vector is just the embedding of each series, and the second vector is just the RNN state at the prediction time t. So using this method, they obtain decent results, and I feel that this is one very sure, very nice starting point for modeling correlations, but it's not the end, and more needs to be done here. So finally, what I have tried to present in this talk is that modern deep learning tools have surpassed conventional methods for time series forecasting, but we still needed to do more. And one of the things that we presented was a hybrid of conventional local models and global deep learning models to get the best of both worlds. And for long-term forecasting, we needed to capture drift, and we did that by having sort of this count model on the side. You can think of it as a guard which would prevent the low level event model from drifting off. And then for correlations, the research community is warming up. There is this very nice approach which has been presented in the form of Gaussian copulas, but I think again more needs to be done here. So this is promise my last slide. So in terms of future work, I think there are a lot of exciting research problems still remaining. So one question is, finally this forecast, as you know, is very difficult. It's very difficult to make forecasts, particularly about the future. So, but so if the forecasts are noisy, how are they used in decision making? Should we change the loss function to sort of be more end-to-end with how the forecasts are used for decision making? Second problem, this is again a problem in which we have some work in-house, is in creating models for outlier detection which are interpretable and configurable to capture users' mindset and interactive. So this is a problem, for example, which government departments might be interested in when they are trying to analyze audit reports from different states. Another exciting area is counterfactual forecasts. So people, it's very natural to ask questions like, what discounts or price or offers will give rise to a particular targeted demand? So these are some problems which are going to be also areas in which me and my group will be working on for the next few years. Thank you very much.
Okay. So let's have a virtual clap. Thank you so much, Sunita, for a wonderful, really fascinating and comprehensive talk. So I'll just again remind people attending the session to post their questions on the Q&A panel. I have actually several questions, but yeah, let me start with a few that have been posted. So I'll start with the question from Abdul Rahman. If you could talk about your papers that you have published on this work, could you just highlight where people can find those papers?
So they are all there on my homepage.
Okay.
So the papers are there on my homepage.
Yeah, and maybe you can just highlight a few of these. I mean, which conference and so on, right? These papers appeared.
So actually, it's like, someone's library was burned. Both of his books were destroyed. So my case is similar in this topic. All the papers that I have that I have worked on, all the relevant papers have been covered in this talk.
Okay.
Okay. So all three papers have been presented.
Thanks. Okay. Then there's a question from Ranjita. To learn sudden spikes that happen only at particular time in the year, you'll presumably need at least 1 to 2 years of data, if not more. So did you have access to multiple years of data? This is referring to the Flipkart example, right? Where you showed, I think it was the Flipkart data where you showed that spike that you could.
Yeah, I think they had access to. So actually, this work was done in collaboration with the Flipkart researchers, and as expected, we did not have access to the data. If I remember right, they had data over multiple years.
Okay, so they utilized that data over multiple years.
Yes, yeah.
And in fact, I was expanding upon Ranjita's question. So typically, I mean, how much of data do you need for those methods, right? That you covered in the first part, where you showed deep learning showing better performance, right, than the conventional machine learning based methods. So in particular, for an example, let's say if we were to do models of COVID forecasts, would we have enough data, let's say for specific regions, just from the data that's been collected over the last year, would we have enough data to allow some of these deep learning methods to be used?
Yeah, maybe not. Maybe not. I think one should be very careful before investing in deep learning. Somehow, I think for COVID data, perhaps simple logistic regression models
Right.
would work just as well. Yeah.
And also things are changing too much, right? I mean,
Yes.
like,
Yeah.
let's say any kind of lockdown or mask and
Yes. Yeah.
kind of vaccination and so on, right?
That's
Perhaps
right. Yeah. And also, these are, we are really playing with life and death here. So I think we want something which is totally interpretable.
in
So
fact, yeah, that was my other question related
yeah.
both interpretability as well as, I mean, I know you have done a lot of work on estimating the confidence in the prediction and so on. So,
Yes.
uh, are you able to do that with these methods?
Actually, I have not evaluated calibration of the regression models. What we have mostly been doing is measuring the CRPS metric, which jointly evaluates the variance. So essentially you're outputting a distribution and we see the likelihood sort of the true value with respect to that distribution. So if you output very wrong values of variance, then your CRPS metrics will suffer. But rigorously measuring calibration, we have not done that.
Okay.
But this is something we are interested in. So I know you are interested in this topic, and I have a
No, I
PhD
know,
student.
yeah, you have done a fair amount of work on
But
this.
not for regression. For
Not for
regression, I know, yeah, there are some papers, but we have not like rigorously evaluated calibration of regression values. Yeah.
Then there's another question from Ranjita, and Ranjita, feel free to jump in directly. Doesn't the efficacy of ARU and RNN assume some kind of relationship or correlation or dependency in the time series for the various items? What if this doesn't exist and each item has independent characteristics in time? Will this technique work?
So actually, ARU will still work because the local models are specific to each time, and the global models sort of you can think of them as learning shared transformations of the input, and they sort of give us the higher capacity. They transform the input features in what we believe is a linear space on which we can then fit a linear regression model. So I think ARU will not make things worse. We have careful sort of regularizers, because when you are fitting a first series a linear model, you can also regularize the parameters. So
Okay,
okay.
understood.
Sorry, Ranjita. Okay. Fine. Then there's another question from Rushil. What is the type? How is the type of event related to prediction? Is it related to severity of or impact of the event?
So you can model that. So far, I was thinking mostly kind of implying that the type of the event is like a class label. So it would be like if you are doing different, if you are modeling different kinds of attacks on your system, it would be the type of the attack. But you can also think of like I was also, maybe I mentioned once or twice that for events you can also have like time. Like for example, for the user visit, you might be modeling users, when a user will come to your site and how long will they stay. So the length, the duration of their stay could be another, you could think of it as the event type if you discretize it. Yeah.
Okay.
And
Then
that
there's
is sort of not, so actually that part is easy essentially, because, one thing, that is what NLP researchers have been doing for a long time, predicting discrete variables. Sequences of discrete variables is what is NLP about. And with event sequences, we have this additional challenge of time, which is actually earlier I was not paying too much attention to this type of data because I used to think that, oh, time, it's a continuous variable. But actually you need to handle time. It's much more challenging to predict the time of events than, for example, the duration that a user will stay in a session.
Then there's a question from Rajiv. How accurate was the demand forecasting for the retail industry, Flipkart, since the results would have been critical to the organization?
Yes. So actually that is, we have a paper on archive where we show that, see, for the retail industry, they will only accept forecasts which have some confidence of being within, say, a 30% band of actual values. So there are some numbers. So this is a data set on which, the Flipkart engineers were doing most of the experiments. So I cannot give you exact numbers, but we have those charts in the paper.
Sure.
Yeah.
Another question from Ranjit. Ranjita, do you want to ask it directly?
Yeah, let me ask this one directly. When people are doing capacity planning, say in a data center, how many machines to order, etc., they do a lot of time series based forecasting to do that. But they are specifically interested in worst case analysis. So they want to provision for the worst case. So when you start thinking of the worst case, do these algorithms fundamentally change in any way? Or does
Yes, yeah, they would change a lot. For example, so far I was maximizing the likelihood of the prediction. But suppose if you want to, make sure plan for the worst case, then you might want to fit, say, the 90% quantile of the data. So it's not like the network architecture would change much, but the loss function would change.
Right. Okay, I understand. Yes.
Okay, are there any other questions? Ashutosh or others?
Yeah, I might like to ask a question. So I'm a networking guy. So my question is, and security. So nowadays we're talking about predictive security. So I'm thinking how some of your analysis algorithm could be applicable where we don't know that you don't have the signature. It's kind of a 0-day attack, right? And depending on the data that you gather, signaling plane, data plane, how can you predict that something is going to happen, right? Have you thought about the application to the network side?
So I think, for the application to the network side, we would have to work with networking researchers. We have, we have people in IIT Bombay, and we should perhaps work with them. I cannot comment unless we actually, because I am sort of also kind of applied researcher. I don't want to glibly say that it's going to work. We would want to try it out. Maybe that.
I'm just thinking that could be another vertical where this could be applicable, right?
Yes, for sure. Yes, yeah.
Excellent.
Another question that has just come up from Dibakar. Can we model prediction of a main event based on previous irregular sub-events?
It's you have to model it. I mean, so far what I have done does not express that, so one has to go into the details of the data, and, everything can be modeled, particularly now with the capacity to handle nonlinear relationship. You give us the data, we'll model. Yeah, it's not, what I have presented, but it seems like it should be possible. Yeah.
Yeah. So on the last slide, Sunita, you had a few of these like potential future work areas, right, which actually I was curious about, right? One was you mentioned kind of instead of the loss function, right, just accuracy of the prediction, the actual impact, right? I mean,
yes.
So do you think, I mean, as you work on those, do you think the techniques will fundamentally change, or would that be just a tweak in terms of how you're doing the loss function modeling?
Actually, I feel that you might need more signals, and like what Ranjita asked, right? For example, if you know that you are interested in doing capacity planning, then your loss function might change, and it might change in very drastic ways. So there is you were in that session where Pradeep Kumar was talking about, you remember that in that Web House Summit, I don't know, Manish, whether you were there or not. So, so maybe there might be, it might change a lot. Yeah.
Okay. Any other questions?
So feel free to write to me if you have any other interesting applications. So we are like shopkeepers. We are sitting with the tools, and we are looking for hammers. So
Manisha, I have a generic question you might ask.
Yeah.
yes.
So the availability or accessibility to the data set, do you see any problem there? Because, I'm talking about that because IEEE has something called data port, where they have the repository of different types of data. So how do you get the access to different kinds of data to do the analysis?
So actually, thankfully, these days with Kaggle competitions, lot of data is available online.
Okay.
Yeah, but of course, it's not going to be as rich as, say, Flipkart's data. But, so initially we were working with them, and then some of the main guys with whom I had a rapport, they left Flipkart. And then, we started working on public data, and that was also okay.
So on a lighter vein, Sunita, I was thinking that maybe with all of this expertise, you could be running an astrology service, right? Fortune telling service. So what's the fortune going to be in 2021? Is it going to be a better year? What do we have
We were just talking, with Showman, and I just, prediction is very hard, particularly with unruly Indians. Sorry, people just do not follow social, just no one follows guidelines. So I think, I don't know what's going to happen.
So there was this joke that somebody forwarded to me today. I think it had to be somebody from the US who said, "Oh, I'd like to cancel my subscription for 2021 because I'm not very happy with the 7-day trial." So, with that, let's again thanks Sunita. So if you could just stop sharing, I'd just like to flash one slide.
Okay. Actually, I think I stopped sharing.
Yeah, actually, you have stopped sharing. Just give me a minute. So, Sunita, this is promise. This is a real plaque, but we are showing you right now a photograph. So, the real plaque should be delivered to you sometime soon. Again, just a token of our appreciation.
Is it with samosas or?
That's right. So again, hopefully, yes, we'll make sure there are a few samosas added as well. So again, really appreciate again this wonderful talk, and again look forward to hopefully hosting you in person sometime in the near future.
Thanks a lot. I enjoyed the interaction. Thanks for the questions.
Okay, I'd just like to make an announcement to the conference attendees that there's a panel which is starting soon, and this panel, sorry, I'll just maybe talk from the memory. The topic is, I think, AI ML applied to networking, various use cases. So sorry, I was trying to look up the precise topic, but it's overall in the area of how AI ML might get applied to the area of networking and looking at various use cases. So I'll encourage attendees to stay on for or attend that particular session. Thank you. Thanks.
Thank you so much.
Bye. Bye.
Thank you. Bye-bye.
Bye.